On a cold winter day, someone starts up a modern GM engine with the wrong viscosity oil in it. Is the engine more or less likely to be damaged than an older low-tech engine would have been? Why? If too much oil is added to an engine, which engine parts are most likely to be damaged? Why? Every year, a lot of used engine oil is disposed of illegally. How much would you guess? Hi, I'm Jim Scopolitas. The truth is, the story of engine oil and how it must change to meet changing demands is a fascinating one. In this program, we'll show why, today more than ever, it's essential to use the right engine oil, which now means one marked with the American Petroleum Institute's new Starburst certification symbol. If you haven't already seen this Starburst on our Good Wrench motor oil, you will soon. We'll also explain why an oil that wears the Starburst doesn't need aftermarket additives, and why some additives could risk engine damage. We'll answer those questions we started with, and we'll take a quick look into the future of engine lubrication. Okay, first, let's review what oil has to do. Obviously, oil must lubricate, reducing friction, to minimize wear and to minimize power loss. Seen under a microscope, even the smoothest surfaces have rough spots. Lubrication greatly reduces friction between metal surfaces by substituting friction between layers of oil. In GM engines, oil is pumped to certain key friction areas and reaches all others by gravity flow, or, as with the pistons, by crankshaft throw-off and connecting rod splash. Oil also helps cool engine parts by transferring heat away from them. Oil absorbs shocks at connecting rod and main bearings. During the power stroke, pistons are driven downward toward the crankshaft with loads of as much as 2 tons. Under this pressure, the layers of oil between bearings and journals must resist being squeezed out. They must stay in place to act like cushions, reducing wear and quieting the engine. In the engine cylinders, oil plays another crucial role. With piston rings, oil must coat the cylinder wall so that the 2 compression rings can form a tight seal with it and keep the high-pressure combustion gases from escaping past. Oil also must keep these rings free in their grooves so they can maintain that seal with the cylinder no matter how the piston moves in the bore or expands and contracts with temperature. Of course, another crucial function of oil is to act as a cleaning agent, keeping dirt, carbon, and other foreign material in suspension until it's caught in the oil filter or drained at the next oil change. In most engines, oil has another task. All domestic GM engines use hydraulic valve lifters, which means oil has a hydraulic function too. Of course, the main job of the lifter is to operate the valve, following the profile of the cam. But it must also compensate for changes in the length of valve train components as a result of temperature changes and wear. It should keep the valve train tight and quiet under all circumstances. The hydraulics in the lifter do that. During the opening of the valve, the lifter body and the plunger inside it, which raises the push rod, rise together as a unit. But when the valve is fully open, the plunger is pushed downward separately, forcing a small leakage of oil upward between it and the lifter body. Once the valve has closed again, oil pressure refills the lifter, raising the plunger as far as it will go. This automatically takes up any clearance in the system. Finally, engine oil must work well at all temperatures and retain its good condition as long as possible. Oil manufacturers modify the refining process, attempting to meet these needs. But no oil can do it all for long. So multi-grade engine oils as marketed already include the following additives: an agent to keep the oil's viscosity from getting too high at low temperatures or too low at high temperatures, a pour point depressant to lower the temperature at which oil becomes too thick to flow, oxidation, corrosion, and rust inhibitors, a foam inhibitor to help keep oil in the crankcase from being whipped up into froth, a detergent dispersant package to keep dirt, carbon, and oxidation products in suspension, and an additive to reduce the wear of parts that are under extreme pressure. All starburst oils also have passed a fuel economy test, which for most products requires the addition of a friction modifier. We'll talk about a few of these needs in particular as we look at 3 potential trouble spots in today's engines: connecting rod bearings, piston rings, and cams and valve lifters. Let's begin with bearings and the thickness of oil. We've said that to cushion shocks in an engine, particularly at connecting rod and main bearings, the oil needs to be sufficiently thick. But even more important than shocks, oil is subject to shear. Oil is sheared when layers of it are forced to move past each other. Shear increases with the speed at which parts are passing each other. Shear decreases with the thickness of the layers of oil. So again, an important goal is to keep layers sufficiently thick. Of course, one thing acting to thin the layers is the load on the parts. At bearings, oil's wedging action can help keep the oil cushions thick. When the crankshaft is still, gravity causes it to rest straight down on the bearing. But when it rotates, it draws oil with it, and the moving oil forms a wedge that lifts the shaft off the bearing and builds up the cushion where it's needed most. Still, everywhere in an engine, the chief key to the oil's thickness, and therefore its ability to resist shear as well as shocks, is its viscosity. And the trick with viscosity is that it changes with temperature. So a multi-grade engine oil includes an additive to keep its viscosity acceptable across a broad range of temperatures. Most GM engines need oil that is graded SAE 10W30 or SAE 5W30. This notation means this oil has an additive that makes it as viscous as both a thin 10W grade oil in the winter, W is for winter, and a heavy 30 grade oil at higher temperatures. Incidentally, at the bottom of this donut symbol, notice the energy conserving 2 designation. That means the oil has passed that fuel economy test we spoke of. And in 1993, this SH replaced SG as the American Petroleum Institute's symbol of currently approved quality. The designation has come all the way from SC since 1967 and will keep changing as engine requirements change. But from now on, the starburst symbol is what GM owners' manuals will specify as the sign of approved quality, and the starburst won't change. Back to viscosity. Obviously, an oil that's too thin at high temperatures may not protect against engine damage, but an oil that's too viscous at low temperatures may not flow quickly during cold weather startup. Today, that's a real problem. In the old days, an engine just wouldn't start if its oil was too viscous. That annoyed the driver, but protected the engine. Today's electronic ignition can start an engine even when the oil's not flowing, and the engine can be damaged as a result. So that's the answer to question number 1. And it means that these days, the low temperature viscosity of oil is very important for protecting parts, including protecting bearings against seizure. But viscosity at high temperature is also important for bearings. The additives needed to make the viscosity of most oils acceptable at both high and low temperatures are polymers, compounds consisting of very large molecules. Let's say this is a simplified polymer molecule. At high temperatures, These huge molecules fluff up, increasing the oil's viscosity. But polymers may not be stable at high shear rates, meaning that when the turning speed is high and the layers of oil are thin, those big molecules may break up or become temporarily deformed by the flow, so that at the very split second we need viscosity most, we may be getting less than we think we are. Tests can measure a product's viscosity at the shear rates experienced by piston rings and cylinder walls and by the connecting rod bearings. But the shear rates occurring between the cams and their lifters are so high that they go off this graph. That's because the loads borne by a cam lobe in its lifter, even a roller lifter, are the highest loads in the engine and may actually cause the extremely thin film of oil between them to act like a solid for an instant. So cams and lifters are tremendously dependent on an anti-wear additive for protection. What we add is zinc dialkyl dithiophosphate to be exact. ZDP decomposes at these high pressure points and actually bonds with the metal surfaces to provide a protective coating. This bonded zinc coating can last for quite a while. In fact, if an owner changes to a lower quality oil without zinc, there may be no noticeable difference for some time, but eventually the trouble will begin. Lifters really are a crucial test for oil. Almost anything that can go wrong with oil can affect them. Let's look at a cutaway of a lifter. And notice the small amount of internal clearance between the plunger and the lifter body. The space through which oil must be forced during each trip up the cam lobe is 3 to 4 microns wide. How wide is that? Well, it's much wider than the film of oil between the lifter and the cam we talked about, which has been thinned by great pressure, but it's still pretty thin. If this circle represents a cross-section of the wire used to make a paper clip, then this is the thickness of the shank of a pin. This is the thickness of a human hair. And this dot represents the clearance between the plunger and the body. Trust me, it's right in there. That means if the oil moving up through this space contained any debris or had formed rust or deposits, they could cause stickiness and wear. So all the additives that inhibit contaminants or help move them to the filter for removal are very important for keeping the lifters in shape. And so is changing the oil on schedule. What else can go wrong with the oil and affect the lifters? Well, if too much oil is added, so the level rises above the full mark on the dipstick, it can be churned up in the crankcase and become foamy. When a lifter's raising a push rod, the oil trapped beneath the plunger must act almost like a solid. If the oil here has air in it, the lifter will act more like a sponge. That'll throw off the operation of the valve, allowing it to bang on its seat and perhaps break. So, to answer question number 2, valves are the parts most likely to be damaged if too much oil is added to an engine. Okay, we've covered quite a bit about engine oil, including the reasons that all these additives are very important. But it's a real trick to get a mix of oil and additives that'll meet all the necessary performance standards. And once it's achieved, it shouldn't be tampered with. That means with a starburst oil, there's no need for aftermarket additives. And some additives could make things worse. For example, as we've said, piston rings must stay free in their grooves in order to maintain a constant seal with the cylinder wall. But they're lubricated only by splash and throw-off. They have no pressure feed oil supply. That means they're especially subject to sticking in their grooves. And there are substances in some aftermarket additives that really could gum them up. In fact, there are a number of problems which some additives might contribute to. So, it makes sense to stay away from all aftermarket additives. Let's close with that glimpse into the future I promised you. One thing we're likely to see is an oil probe that can directly sense oil condition. It'll probably be able to detect low-quality oil, detect a coolant leak, and report when the oil actually needs changing. With a very good oil, this could mean at significantly longer intervals. That could really help the environment, because the truth is, we're in an environmental bind. While oil must be changed often enough to protect engine parts, disposing of used oil is a major environmental problem. Illegal disposal is a worse problem. The amount of oil that's illegally disposed of each year equals more than 35 times the amount spilled in the Valdez accident in Alaska. And that's the answer to question number 3. We must find ways to reduce the amount of oil disposed of, both legally and illegally. One thing that might help us do that would be increased use of synthetic lubricants, like the Goodwrench synthetic used in Corvette engines. Synthetics are more expensive than mineral oils. That fact, and the fact that they may prove more reliable in recycling than mineral oils, could be strong incentives for developing methods of recycling them. And good synthetic products really do offer many advantages over most mineral oils, including these. So, in the years to come, watch for synthetic lubricants and major developments in recycling. Meanwhile, tell customers to look for the starburst and then to forget about aftermarket additives. What's needed is already in there. See you next time.